In this video, I'll be talking about benzene directing groups if there are multiple substituents. For example, let's say that we have this benzene and it has both a chlorine as well as some kind of ketone on it. As we know, chlorine is electron donating, whereas this ketone is electron withdrawing. And if we kind of use my hack on how we can tell whether it's electron donating versus electron withdrawing, remember that I just talked about just looking at the electrons. So chlorine has extra pairs of electrons on it, thus it can donate electrons. Conversely, this carbonyl group, right, we can draw a resonance structure, and when we do so, we know that this carbon is going to have a partial positive charge. So because we have both an electron donating as well as an electron withdrawing, the question becomes, does this go with the order of the electron donating group or with the electron withdrawing group? So in this slide, here's the order of determining the location of the reaction. So the first and most important is that orthopara will always be prioritized over meta. And the reason for this is orthopara gives an additional resonance structure, whereas meta just wants to avoid an unfavorable resonance. So giving it an additional resonance structure is going to be more stable than just avoiding, a bad resonance. So because of that, orthopara is always going to be prioritized over meta. The second criteria is that it's always going, if there are two orthopara groups, it is always going to be closer to the stronger orthopara directing group. Likewise, the third criteria is if there are two meta directing groups, it's always going to be farther from the stronger meta group. And the last criteria is that it's always going to avoid sterics. In other words, if there are two groups on a benzene that are relatively close to another, the substituent probably won't add to the adjacent side so that there won't be three groups right next to each other. So if we go back to the original problem, the first step is to always identify what kind of group it is. First, we know that chlorine is an electron donating group because, as I mentioned, it has electrons, thus it is an orthopara director, whereas this carbonyl group is an electron withdrawing group, and thus it is going to be a meta director. So with this information in mind, we have to determine whether this nitration reactant is going to be in relation to this electron donating group or this electron withdrawing group. And if we go back to the previous slide, I mentioned that orthopara is always going to take priority over meta groups because orthopara can give an additional resonance structure. So with that information in mind, we know that this reaction is going to be in relation to this electron donating group. And we know that electron donating is orthopara, so this nitration is going to be either on this ortho position or this para position. Because this para position is already taken up by this group, we know that this nitration reactant is going to be added onto the ortho group, like so. For this next problem, the first step is to identify whether these groups are orthopara or meta-directing. So starting with OCH3, we know that this oxygen has extra pairs of electrons, thus it is electron donating, thus it's an orthopara director. Likewise, this methyl group is also orthopara because these hydrogens give the carbon extra electron density. Thus, it is also electron donating, therefore it's orthopara. So because there are two orthopara groups, the question becomes, in which relation does the nitration reaction go upon? Is it the OCH3 group or is it just the CH3? So if we look back onto the chart, The second rule is that if there are two orthopara groups, it's always going to be closer to the stronger ortho group. So with that in mind, we have to determine which orthopara group is stronger. So just by looking at it, this methyl group is kind of a weak orthopara group because this OCH3 has actual electrons on it to donate, whereas CH3 doesn't really have extra electrons. It has extra electron density, but not electrons itself. So because of that, OCH3 is the stronger orthopara group. So because of that, we know that this nitration is going to be placed on the orthopara group in relation to this group. So as like the last problem, the para group is already taken up by this methyl. Thus, this can only be placed on the ortho group. So when this reaction proceeds, the following molecule is going to look something like this. So, much like the last problems, the first step is to first identify whether these groups are orthopara or meta-directing. So we know that OH is going to be orthopara because there are extra electrons on the oxygen. Thus it is electron donating, thus orthopara. Conversely, NO2 is a meta-directing because NO2 has a positive charge on this nitrogen. If you need to draw it out, here is the benzene, which I'll just notate with Be, the nitrogen, and there are a double bonded oxygen and an oxygen here. Because of that, there is a negative charge on one of the oxygen and a positive charge on the nitrogen. So because of the positive charge, we know that this is going to be electron withdrawing, thus it's going to be a meta-director. So if we go back to the chart, one of the rules is that the orthopara is always going to take precedence over the meta group. So, with that in mind, we know that this reaction is going to take place in relation to this OH group. So once this reaction proceeds, the following molecule is going to look something like this. And for our final problem, the first step, as you know, is to identify whether these groups are orthopara or meta-directing. So we know that NO2 is going to be an electron withdrawing group because of the reasons I stated in the previous problem, and carboxylic acid is also going to be an electron withdrawing group. And the reason for this is if we draw out the molecule itself, here is the benzene, which I'll notate with Be. Here's a carbon. There is a double bonded oxygen here and an OH, right? Although the carbon itself does not have a positive charge, we can draw a resonance structure like so, thus resulting in this molecule. So because of this, additional resonance, this carbon has a partial positive charge. And because of this partial positive charge, it is electron withdrawing. So, because these are both electron withdrawing, the question becomes, in which, relation does it take? And the answer, if we go back to the chart, the third rule is it's always going to be farther from the stronger meta group. So with that in mind, we know that it's going to be stronger from the stronger, it's going to be farther from the stronger meta, aka electron withdrawing group. So the question is, which one is stronger? And the answer is NO2. And the reason for this is, as I mentioned in this here, the nitrogen here has a full positive charge, whereas the carboxylic acid only has a partial positive charge because only one of the resonance structure has a positive charge, whereas this one has a neutral charge. So because this nitrogen has a full positive charge, this is going to be stronger. So we know that this is going to be meta to this NO2. So if we locate where the meta position from this NO2 is, one meta group is 1, 2, so one position could be here. And the other meta group could also be here. So now the question is it going to be primarily here? Is the meta group going to be here? Or will we get some kind of racemic mixture that will do both? And if we go back to the chart, the fourth and final rule is that it's always going to avoid sterics. In other words, you want to avoid having a lot of groups right next to each other because that's going to be, very bulky, and that's also going to lead to sterics. So, with that in mind, if we were to add the molecule in this position, we would have 3 molecules right next to each other. And as we know, that is very bad. Conversely, if we were to add the Br here, this would avoid having 3 groups right next to each other. So because of that, this is the much more stable position. So once this reaction proceeds, we are going to get a molecule that looks something like this. So, as I mentioned, the Br is going to be added on this position rather than the other position because this avoids having 3 molecules right next to each other. Right? In actuality, you probably might see like a 99% of this and like a 1% of having the bromine here. But the bromine is primarily going to be on this position, so this is the main structure you would write.